Hello, everyone. Welcome to my presentation on some geometric aspects of robotic systems, in particular floating base and space robots. And the topic is what we call differential geometry, or let's say geometric mechanics. And first of all, I would like to thank the organizer of the workshop for inviting me. I guess it's a bit of a different topic. It's not so much, if at all, on artificial intelligence, but it hopefully shows you a bit of the other side of science in nonlinear dynamics, because model-based control, model-based methods for modeling and control, they have been there for a long time, maybe a century, and there's lots of things out there that can be used and should be used also in conjunction with methods from artificial intelligence. And without further ado, let's see what we mean by a robotic system. And when we talk about a robot, then usually we think about first of all mostly these kind of industrial robots that are supposed to do some sensible work. They usually are supposed to move fast and do things in a certain way and in some way intelligent, whereas the intelligence usually is quite limited in a sense that they repeat what you have been programming, and the motion is always more or less the same. But that's going to change, and it has changed in the past. So these systems are more becoming more adaptable and more, let's say, aware of the environment, that they react to certain conditions in the environment change, and also they are now more intelligent in the sense that they can handle objects and manipulate in unstructured environments. So much more advanced than what we had in the let's say the era of automation in the last 30 or so years. And there are, of course, a couple of problems, or let's say a couple of issues that we have been working on and that are still on the agenda, which is this thing that you see here, which is called a singularity. It's pretty simple in this case. When you stretch it, then the system becomes a bit unstable, and that has to do with the kinematics, and that is something that has to do with the geometry, and in turn this has to be addressed by certain modeling. And this is again the emphasis on modeling. I haven't seen much on this in terms of artificial intelligence. What you see here also is a system that is called a cobot, a collaborative robot, in a sense that it can collaborate with a human. So first of all, you are actually allowed to touch it, and secondly, it has a sensor, in this case, and the so-called end effector. This is the end here, and it can sense the torque and the force that you apply to it, and it certainly does react somehow. There are other systems that has a different topology in the sense that we have here closed loops, closed kinematic loops. So what you see here is like an open kinematic chain, as we call it, and here we have closed loop systems. It's just a different thing. We call them parallel manipulators or parallel kinematic machines, something that you might hear about or may hear in the future again. So let's get into the modeling topic here. So first of all, it's a very simple thing actually. How do you represent the pose, or let's say the configuration of a body, of a rigid body in space? And that has to do with two things, which is the rotation and the position of a frame, and a frame that is attached to a certain body, or sometimes we call them links on the manipulator, right? And the rotation is usually represented by a rotation matrix, and the position vector, and the position by a position vector. The first one is an element of the so-called special Euclidean group in 3 dimensions. We call them SO3, and the other one is just a vector in R3. And there are different ways of actually representing it. It might be surprising, but there are still different ways of looking at this. And the one is that we call this the semi-direct product. In a sense, pretty simple. So you put them together, you have the tuple of the rotation matrix and the position vector, and now you can say they're living in a certain space again, and that space is now what we call the SE3. And this is something that is a Lie group. You might have heard about Lie groups, or you might not have heard about Lie groups, but you're going to hear this more and more frequently now in science and also in the learning aspect when it comes to manifold learning and these kind of things. And this is a very special kind of Lie group because it's a so-called semi-direct product, whereas you can also say this is a direct product. What's the difference? Well, the difference is if you look at a combination of rigid body motion, so let's say the combination of the frame transformation from one frame, let's say F1 to F2, and then from F2 to F3. If you combine them, then what you expect in the proper kinematics is that you of course combine the rotations, the one comes one after the other, whereas the position is of course influenced by the rotation. When you rotate the body, then of course it does have an effect on the translation of a generic point, unless it is the point about you rotating. But usually that is having an effect, and this is why we have this term here. Whereas if you say that we use this so-called direct product, it's just the sum. There are legitimate reasons for using either of them, and we will see what the consequences in a minute. But maybe a takeaway message is the proper way of describing poses is using the SE3, the semi-direct product. And usually, and this is what you might certainly are aware of, we like to use this these matrices that are called homogeneous transformation matrices, where we put them everything, the rotation matrix R and this small, the little r, the vector, in this 4x4 matrix. And the good thing is that now the combination of the frame transformation is simply by the matrix multiplication. So you just multiply one after the other, and then what you get is the transformation from the one frame to the intermediate frame, and then from the intermediate to the first frame. So that's a bit of a setting. And within this geometric setting, which is just repeating the very basic kinematic relations from an undergraduate robotics class or multi-body dynamics class, in terms of a maybe a bit more fancy notation using this SE3, but essentially it's all the same. But the reason for doing is that there is much more behind this, because there is a bit more geometry behind it, because it is a Lie group. Now, if you look at how you generate or how you parameterize these kind of 4x4 matrices, there is a nice way of doing is using an exponential. And this exponential is, of course, supposed to return a rotation matrix. This is that one here, and the position vector. This is just the one here, where we have the differential of the exponential mapping. In a bit more detail, so this one, the first exponential is the one on the rotation group, and this is usually called the Euler-Rodriguez formula. So you plug in this little x, which is the unit vector along the rotation axis times the angle, and then what comes out is the rotation matrix. And this is just a differential of this. And that's fine. For the exponential map on the direct product, this is of course pretty simple, much simpler, because you just have the rotations, and then the translation is just the parameter that you're using, because it is not affected by the rotation. Now, the semi-direct product can also be used to define velocities, or we call them twists, in a consistent geometric setting, in the sense that we not use some sort of kinematic reasoning for introducing velocities, but we use what we call left and right translations of the differential. So we have just this kind of expression that you might remember from the definition of the rotation of the angular velocity by this formula. So you can generalize this to the SE3 Lie group, and this is the formula here. And then what you get is again a 4x4 matrix that corresponds to a 6 vector, where we have the angular and the linear velocity here. And you can do this, of course, in different ways. You can multiply it from the left and from the right, and what you get is either the base, the body fixed, or the spatial velocity. Okay, and you can, of course, do the same with the I was about saying you can do the same, of course, with the direct product, but let's not go to this. But let's ask, how do we solve this equation? Let's say that they are given, for example, a twist, or let's say a velocity. How do I reconstruct the pose? I mean, how do I reconstruct this homogeneous matrix C? And that goes via an interesting relation, which is this differential equations on the Lie algebra. So by using the Dex mapping, the differential of the exponential mapping, and this has a long history. There are different reasons for using it, and different contexts where this is used. In particular, in flexible multibody dynamics, this is becoming more and more important. But let's keep this for the minute. Let's say that there is a nice differential equation, and this is, by the way, a linear equation, so it should be easy to solve, actually. That is something that we might use later on. And there is something that is, I'm sorry, there is apparently no animation here. Let's maybe do like this for the time being. So there's an important relation, which is called the product of exponentials, or let's say POE abbreviated. And this is just combining these exponentials, because if one of these exponential mappings is doing a frame transformation, then you can, of course, combine these frame transformations. And what you can do, you can actually describe the transformation within a robotic system, like that you have many links here, and each of these, the joint motion is described by an exponential. And what goes into the exponential are the so-called screw coordinates. Without going into detail, these screw coordinates are just some very simple vector expressions that define the geometry of the joint. You plug this into the exponential. What you get out is for example, for this joint here, what you get out of this exponential is the relative motion of the two bodies connected by this joint. That means that you can do the same for this joint. And in the end, what you can do, you can, of course, line this up, and what you get is a formula for doing exactly the full kinematics, in the sense that you combine all these relative transformations, and then in the end, you just need to refer this to the reference configuration, because by nature, everybody knows this. When you plug in 0 as an argument in the exponential, what you get out is, of course, the identity, and that, of course, is not usually what you have, but you have some sort of an initial configuration of each of the frames relative to each other, and in particular, when you have this end effector here, because what this formula, for example, is describing is the configuration of the end effector, a frame attached to the end effector relative to a space fixed frame, right? And this is, of course, not the identity when the joint angles are 0, but is whatever it is here in the 0 reference configuration. So that's about the kinematics. So this is the setting. And by the way, this is sometimes referred to as modern robotics. That might be a bit of an overstatement, because, of course, this POE, this product exponential, has been there since '82. It became more popular since Roger Pocket published this in a small, actually just conference paper in '84, and now everybody uses it. And if you look into a robotic journal, then you're likely finding this POE formulation. Now that's the kinematics. Let's go into dynamics, because as I've been showing at the beginning, these systems, they move with high speed and so on, and so they're moving with high dynamics, so highly dynamic motions. So let's start with a very simple expression for the dynamics. Let's say the Newton-Euler equations just for a single body. And there's a nice way of writing this. Let's see what we have here. This is the kind of a system of 6 equations, and essentially what they are combining is, what they're summarizing, are the momentum balance. So these are the Newton equations and the Euler equations. So It's the angular momentum and the linear momentum balance, what you have here. And again, this is just a kind of a fancy way of writing what you know from your undergraduate course in dynamics. So because what we have here is just a mass matrix that has the inertial tensor of the body, and there's dBc is just the vector from the reference frame to the center of mass. That's all you need. And by the way, this, if you multiply this out, this is the standard equation that you have for the Newton-Euler equations, where the first one is the Euler equations and the second one is the Newton equations. They look a bit more complicated because we are using an arbitrary reference frame. If, for example, what you might have done in your class in school is to use a center of mass frame, then of course this becomes 0. So essentially, you only are left with this term, and also this would cancel out, and you're just left with this, which are the standard Newton-Euler equations. So good thing is that there's a nice way of actually combining this into a bigger system. I mean, combining the Newton-Euler equations for the n individual bodies to a bigger system of motion equations, dynamic equations of motion for the complete system, and that goes via the Jodot principle of virtual power by using that variation here. Okay, so what that is actually, we have seen, no, we didn't have, but there is a Jacobian that relates the twist of body I to the generalized coordinates. This is always possible, but you can always say, let's go back here, you can always say that the twist of each of the bodies, like the body fixed twist of each of the individual bodies, can of course be expressed in terms of the joint, in the joint rates. Like if you call this Q1, Q2, Q3, and so on, then of course the time derivative of joint angles in this case gives via the so-called Jacobian the twist of the individual bodies, and that's what we actually use here. And then by combining all these Jacobians in a big matrix called MJ, then we get this kind of equations, and in the end you can actually refer to this equation as maybe the Euler-Jodot equations, but then summarizing this in a more compact form by introducing this equation here actually into the individual, for the individual, I mean, plugging this in for the individual twists here and the time derivatives, what you get here is a very compact form of the motion equations. This is the standard form of motion equations, where we have generalized mass matrix, the generalized acceleration, the Coriolis term, and some generalized force. The good point is here, and that has to do with the computer implementation, that these matrices are given explicitly and more or less algebraically by these expressions, and they are quite simple. The big M is just combining all these mass matrices and so on, and there's a kind of a triangular matrix that does frame transformation. Without going into detail, you can look this up. Maybe this is not our real topic here. I would like to proceed more to the so-called floating-based system. A floating-based system is pretty much as the same as a stationary robot. It's just a robot, but not fixed to the ground, but somehow the ground, or let's say the base is moving. That could be like a mobile platform. It could be a space robot. It could be a humanoid, where this is actually, I mean, I refer to this plate, for example, is moving in space. So you have the kinematic chain that is actually mounted on a moving plate or moving base. And the kinematic modeling goes more or less the same. And maybe go briefly over the slides here. The only thing that changes is that now you have this the motion of this base frame relative to the inertial frame, this base fixed frame, somehow not constant but changing, and this is called CB, the base pose, as a function of time. And again, this is an element of the SE3 because it's of course a spatial motion, and there is a corresponding twist to this. And what happened in the end is that of course we can do the same trick, or it's the same formulation that we had before. We have the motion of each of the bodies relative to this moving, in this case, base fixed frame, described by the exponential mapping. The only thing that is to be added is, of course, that in the end, the base motion has to be multiplied before actually this CI. So in the end, we have a form that is very similar to what we had before. And now the whole system configuration is described by this, what we call the maybe generalized coordinates. Still, we have the joint angles now called theta and the base pose CB. And that's it. And the corresponding twist is the same time derivative of theta, and then we have the base twist. And these are so-called non-harmonic velocities in the sense that we cannot derive this VB as a time derivative or something, but that's not important. What is maybe interesting if you're interested in that, is that the configuration space is now what we call a principal bundle, in particular a trivial principal bundle, in the sense that we have this Lie group times the joint space. The joint space was just the n tuple of the joint angles in this case, but now we have again in addition we have this relative configuration of the base relative to the inertia to the space fixed inertia frame, and that's why we have this SE3 times Vn, and that has a nice geometric structure. So in the end, the motion equations look very much the same, and the mass matrix and the Coriolis and so on that we had before, that remains as it was. There's just a little addition, not going into detail, but you can do this all in a nice computer implementation. By the way, if you're interested, let us know. There is an implementation in MATLAB at the moment, but we are working on another one for C, and that's it. So the equation here, this equation here governs again the dynamics, whereas now we have here, of course, to take care of the kinematics, and that is the maybe this mapping that I was alluding to before at the beginning. So this is the relation with this differential of the exponential, where we get here differential equations for x dot. So this is the canonical coordinate that goes into the exponential in order to reconstruct, that's why it's called reconstruction equations, to reproduce, so to say, the motion of the system, because what you get out of this equation is just the velocity, and out of the velocity you get the pose. You see, this is a kind of a two-stage formulation. So now the interesting thing here, this equation, is that these equations, but also this mass matrix and the Coriolis term matrix, the M and the C, that they are partitioned because you can split this according to the equations for the base and for the kinematic chain. And this MBB that has it serves as it serves different purposes. And first of all, it is called the locked inertia matrix of the system, because what you can imagine is that this is actually representing the mass matrix or the inertia matrix of the floating wave system if the joint angles would be locked. It's like a one single rigid body, but with the current poles as it is according to the joint angles. And from a more geometric point of view, these equations here, they're split according to these mass matrices, and these mass matrices and the equations, they give rise to this kind of different set of equations. The first one is, again, this is the Newton-Euler equations, right? One in differential geometric terms, these are called Poincare equations, whereas the last n equations are just a simple Lagrange equations. Okay, that's fine. There is much more behind it. Maybe we don't have time to go into the detail here, but the interesting thing is that you can write this also in terms of the structure constants of the Lie algebra, but that's maybe not so important. What is important is the application aspect. So I'm sorry. Okay, I'm not able to do this apparently. So the splitting is interesting because let's say that we look at the first equation. The first equation was one that governs the dynamics of the base. Of course, this is not they are coupled, right? You see here the base twist and the arm accelerations, they are coupled. This is a dynamic coupling. But anyway, so the first one is describing dynamics of the base, and what you see here is what is on the right-hand side is a wrench, like a force and a torque. That is actually the one, the torque and the force, the wrench, corresponding to the motion. And what I'm saying is that what you could do actually, you could ask, okay, if I know the motion, if I plug in all the motion that I'm having, like look at this mobile system here. It could be also a floating base or walking robot, for example. So when you know how it is moving, then you know the twist of the base body, you know the arm motion, so you know theta of t, and what you get out is the wrench. This is the wrench at the base that is necessary to stabilize the system. What you can do, for example, here in this application, is you can find the zero moment point, and the ZMP, the zero moment point, allows you to make statements about the stability of the system. And that gives you the full dynamics. So you know exactly whether or not your system would fall over or not, right? And that's an important point. There's, of course, an interesting area, which is, let's say, call it space robotics or something like this, where we have systems floating in space. And also the humanoids is an example where we would like to somehow decouple the equations in a sense that we would like to decouple the base dynamics from the dynamics of the kinematic tree structure, let's say the robotic arm on top of it, for example. And this goes by the so-called locked velocity. So the locked velocity is simply defined as you see it here. So it's just defined as that velocity of the base that generates the same momentum as you currently have due to the base motion and the arm motion. Okay, and this is why it's called locked velocity, because the locked velocity is simply, you can imagine if you suddenly lock the joints, then this is the velocity that the system is going to attain. Well, you can solve this equation here in a sense that you pre-multiply with mv inverse, and then you have an explicit form for this. And again, this has a bit of a geometric meaning. I'm not going into detail, but the important consequence is that the mass matrix is decoupled. And in the end, what happens is that you have that your systems, the base dynamics and the arm dynamics, are decoupled on the acceleration level. And that is important because of the because for control, and that has a long history in humanoid robotics, and that refers to the so-called centroidal dynamics, where people like to independently control the center of mass position and orientation, as well as the arm motion. But there's a bit of differential geometric background here. I'm just throwing this name in, the curvature of a mechanical connection, because this A matrix that is simply defined like this, that has a bit of a meaning that is having far-reaching consequences, which is called, the meaning is it's a connection on that principal bundle, and there's something called the curvature. And the point is that this curvature vanishes if and only if the momentum is integral. And that's never the case usually for space robots. And that is a big headache, because that means that the locked velocity cannot be used actually to reconstruct the motion of the system. And that is something that people have been working on for a long time. And the same refers to the centroidal dynamics. Okay, I'm not going into detail here. The centroidal dynamics is simply, it's much more the same. It's just saying that instead of defining the locked velocity relative to the base fixed frame, they're using a frame that is currently, that means all the time, located at the center of mass of the system. The total center of mass of the system. The consequence is the same. You cannot reconstruct it, but the advantage is that if you look at the equations here, you just have a very simple equation for the translational. For the Newton equation, the Euler equations are decoupled from the Newton equation, and that is good because from the velocity of the center of mass, you can easily reconstruct the position. But what's not possible again is to reconstruct the orientation. And this is what people have been working on for some time. Maybe I'm not going into detail here, just finally, because it's a bit of running out of time, what you can do is you can use this curvature I was saying, right? This appears in the motion equation. What you can exploit this for reconstruction. Reconstruction in the sense that what you can do is you can actually, when you have a free-floating system in space, for example, what you can do is you can use cyclic motions of the joint angles. And in this case, it's a satellite is having just flywheels, but it's the same kind of kinematics. You can also say this is a robot floating in space. You can have cyclic motion, so you're actually in the end not having moved at all. But what happens is that your robot, in this case a satellite, is reoriented, because what you see here, in the end, it achieves a net orientation. So, and this is used for reorienting the systems in space, and that's called the geometric space. So what you see here is the change of the center of, I'm sorry, this is the change of the base frame after one full cycle rotation. And you see it is moving, and this allows you actually, for example, here for this space robot, it allows you to reconfigure, to change the pose of that robot. You see what we have here, we have just cyclic motions up and down of the arm. But if you look at the base, in this case, very simple example, and I'm going fast forward, what you see in the end, the base has been, the base orientation has changed. So the net orientation has changed in the end. And that is the important thing. And you can do this, you can do this, of course, for other systems. And what happens, for example, here is that you have a space robot that is one that has been designed by the DLR, and you can use this arm motion. You can have cyclic motions of the arm and realign, for example, that spacecraft here. Okay, and you can do optimal control, of course, and this is what we have here. Just the message is you can do this, of course, in an energy optimal way, and not going into detail, but it's just saying that you can do this in an optimal fashion. And in the end, it works. And with this, I'm happy to possibly answer questions if you have any. Because the time shift might not allow us to have a discussion. But if you like, you can always write me an email, and I'm happy to answer any questions. So thank you very, very much for the kind invitation.